So the other cool thing about this is basically what you're designing for. So yeah, it looks all cool and fancy. You put it as a desktop background if you want, but the main thing is go over to the simulation tab and go ahead and hit new simulation. We're going to pop up with this window here. Okay? So this gives you the ability to type in any parameters you want for a launch situation. Okay? So we can adjust the wind speed, basically some weather characteristics, and then we can even get really fancy and do launch cycle. Really, we don't mess with any of that. The main thing we would do is edit the launch rod over here. So our launch rod, if you guys see, we obviously have to launch the rocket vertically. So we can't just like set it on the ground and like run away and hit a button really fast. We have to put it on, it's actually a piece of 80-20. I don't know if any of you guys have worked with 80-20. And we have two buttons, rail buttons on the side of the rocket. And those slide down in 80-20, and then rocket launches off there. Okay? So we wanted to edit the launch rod length because that would affect basically our stability off the rail at like initial launch. Okay? So if we run the simulation here, we can see that this last simulation, we have a green check mark, which means we're pretty set. But if we look, it gives us a lot of good detail. So velocity off the rod, that's another thing that your rod length would affect. So if I went ahead and bumped that up to say an 8-foot rail, then that would certainly be affected. Apogee is of course your highest altitude you reach before you come back down. And velocity at deployment is when you're actually deploying your parachute. So if you're doing these simulations and you see, like let's say we flip those two, and you said 555 feet per second was your velocity at deployment, you really think your parachute would do anything? Like it's just going to get ripped out and then zipper your rocket, so it's just going to basically pull your rocket into pieces, right? So you always want to pay attention there. And max velocity, of course, self-explanatory, max acceleration. Time to apogee. This is another important one because basically by simulating your rocket, an open rocket, you can see time to apogee, which would help you choose your delay charge for your rocket. So we'll get into the details later when you guys actually get your hands on some motors. But you can grind out some of the powder and lessen your delay charge. So say it's 12 seconds to apogee. I wouldn't want to design a delay charge to deploy at like 8 seconds, right? Unless my bird time is 4 seconds, but we'll get into that, right? So anyways, that's pretty much like a quick rundown of Open Rocket, right? So we'll use this to do a little bit of simulations for our main rocket. We're really looking forward to trying to get some CFD and computational fluid dynamics and some finite element analysis also. So anyways, any questions? Nothing? Nobody wants to design level 1 rockets? So like I said, this is free software, so go ahead and download it. It'll really be, you'll be a big help to the team and to yourself to basically design all sorts of cool stuff. We got together on one day and designed all of our rockets in Open Rocket, did the simulations, went and launched them, and everything went just as planned except for our motor problem. Okay? So, yeah, I don't know about that one. All right. Sweet.
Okay, yeah, so up next is Colin. He's going to talk about recovery stuff.
If I haven't met you before, my name is Colin. I'm a recovery team lead, and I'm just going to go over some basics of recovery. I'm actually going to be having a meeting tomorrow. I'm going to be having a meeting tomorrow at Library West. We're going to be going over some of like the initial design phases. It's at 5 o'clock in room 230. And I just want to give you guys an overview before tomorrow so you have a working knowledge with recovery and what it's about and how it works. So basically, recovery, we need to design a reliable system that can safely recover the rocket so that we can be able to reuse it and continue testing it. Consistently return the rocket to the ground without damage to the rocket or objects on the ground. We're not so much concerned with objects on the ground because we test these things in like fields in the middle of nowhere. So we're more concerned about returning the rocket safely so that we can continue to test the payload and recover the data. So, okay. Possible configurations for a recovery battery system. A featherweight design is basically, in like a perfect world, just a very light rocket that just flutters back to the ground. Obviously, that's never going to fly for us. It's more for model rockets that are made out of paper. So the next possible system is tumble recovery, which is similar to a featherweight design, except you're actually inducing the roll. So you have some sort of system that deploys and causes the rocket to roll, and the tumbling makes it slow down so that it's recoverable. It's not practical on a larger rocket. Again, that's more for smaller designs. Nose blow recovery, basically getting sort of closer to what we do. You eject the nose cone, but it's just the nose cone dangling from the rocket that actually slows it down, which again is not very controllable and not very practical for a larger rocket. What we do is we use parachutes. They're ejected from the rocket using ejection charges, and it increases the drag, gives us a reliable, safe recovery. Additional methods you can implement are glide recovery, which is an airfoil, like a wing will actually deploy and cause it to glide down. I mean, that can be done, it's just difficult. Again, parachutes are the most practical, the easiest way to implement. Another possible way is like a helicopter-style recovery, which is blades are deployed, and the auto-rotating of the blades cause it to sort of glide down. I don't know if you're familiar with like a gyrocopter, which essentially it's like as it's falling down, the blades are just spinning, so it's eating up into the energy and causing it to come down slower. The way we configure our parachutes, the system we use is dual deployment. But basically that means we're going to have two parachutes that are deployed to give us a safe and consistent result. The dual deployment allows us to not have the rocket drift too far downrange. You can see that with the first parachute it's coming down steeper, and then the main parachute gives us the soft landing, but not too far away from the launch site. All right. Yeah. Okay. So the first step of this is it's going to go undergo power and unpowered ascension. Basically, the rocket's going to undergo motor burn. During motor burn, any stable rocket during ascension is going to naturally orient itself into the wind. Okay, so depending on what the wind speed is, it's going to be traveling farther downrange, or not that far downrange. It just depends on the wind speed. But what you can see from this is actually an open rocket, which he was just showing you. This was for my level 1 rocket. Basically, you can see like motor burns here, the motor burns out there, and it continues to coast up until apogee, and it's drifting downrange, about 70 or 80 feet, and then at apogee, the parachute goes out, and then it drifts all the way back down here. So this is useful for calculating its position, where it's going to land. Obviously, we wouldn't want to do something like this for our actual rocket, because the altitude that the parachute would deploy, it would coast so far down, it would just be ridiculously far off. So that's the whole reason for the dual deployment system. It's basically the slope of this line is going to be really steep at first, which is going to be descending really quickly, and then the main parachute comes out and causes for like a slow landing, but it's not that far downrange. So yeah, that's that. Okay, and then for a level 1 rocket, it's to deploy the parachute, the initial parachute. It is a time with it uses a timer. It's actually part of the grain. You were talking about the ejection chart. You adjust it by how much material you drill out of this particular piece, and that adjusts it. So you have to know the exact time from launch until apogee to be able to deploy the parachute. That's not for our design. We use an altimeter which can find when apogee is and control the charges themselves. So we don't really have to worry about the timer. But for the timer, that's an important reason why we use Open Rocket, is we can actually see the time to apogee so that we know what to set. the time from the timer to set off the first parachute. Okay. We find apogee using our altimeter. The one we use is the strata logger, and it gives us fairly consistent results. The ejection charges are actually controlled by this. The drogue and the main are both controlled. So yeah, it's been giving us fairly consistent results. So that's the altimeter we use. The ejection charges, we have been using like a black powder substitute pyrodex, but we're going to be trying out some different ideas this year. Basically, at apogee, these ejection charges go off and deploy the drogue parachute. The ejection charges break these shear pins, which are these pins you see here. Basically, they're pins that are designed to fail. They hold the rocket together until it needs to break, and then they shear. So we use those to keep the rocket together. At apogee, when the ejection charges go off, they shear and release the parachute. So, yep, that's about that. We're looking, like I said, for some different types of charges. We're just exploring options. Here's a video of charge testing. See if it's over. So that was for the hybrid rocket, but it's the same concept. That was the charge test for the ejection charge for the parachute. All right, so the first parachute to go off at apogee is the drogue parachute. And for our project, we use a smaller one. It's an X-form parachute, and you can sort of see it off to the side down there. It's much smaller. And it's not really round, it's more like a jellyfish shape. It allows us to lower the speed so that it's not like coming in ballistic and uncontrollable, but it also doesn't have like a horizontal drift downrange. It's ridiculous. So basically, it's not going to like take the rocket like miles downrange. So it allows us to still be able to recover it. Selecting parachute size. Essentially, we have the drag formula, just the weight, we set them equal to each other, and we solve for diameter of the parachute. And that allows us to select an appropriate size for the parachute given those parameters. You can also solve for velocity if you have the diameter. So that allows us to give us a good working some numbers to work with for selecting parachute size. All right, so after it's coming down on the drogue chute, it's coming down fairly steep, it's coming down pretty fast. And at the second event, for our rocket, it was 700 feet. The altimeter will see that it's at 700 feet, deploy the second charge, another round of ejection charges will go off, and deploy the main parachute, which is substantially bigger and will give us a nice descent rate for landing that won't damage the rocket. Main parachutes, like I said, much slower descent rate, detonated at a specific altitude. You can see that it's really big actually. And then finally, we just have to locate and recover it. For this rocket, we need GPS coordinates because it can vary so much, the location. Obviously, we try and model it, but last year we had some success finding it with GPS location. We were actually able just to punch it into like a GPS navigation system and drive to this guy's house, literally. Rocket was sitting in his backyard. So, yeah, it's an invaluable tool when it works, the GPS location. And for high altitude rockets, it's definitely something. So I think that's about it. Oh yeah, here's that meeting for tomorrow, where I'm going to be going over some of the initial design phases for recovery. I mean, it'll be a good way to get some design experience and just start working on the engineering process. It's going to be tomorrow, 5 p.m. Library West, room 230. And does anybody have any questions? I know I sort of flew through all that. So,
Is that for like big rocket, or is it for
yeah.
or in general?
I mean, this is going to be for like the subsystem for the bigger rocket. But I mean, it will be good for like any sort of.
Thanks. So I know that was a lot of information thrown at you pretty quickly. So thank you all for hanging in there and sticking with us through all that. There's not a whole lot left. I just want to go over some of the upcoming meetings. Just moving forward. Right after this meeting, Crystal's going to hold a quick propulsions research thing just to talk about all the different variables she wants to look at going forward. So that's something that we can do right here. Stick around after the meeting if you're interested in that. If you're interested in the CAMSAT project, Lauren's going to have that meeting next week on Tuesday at 6:30 at the Energy Park. And our next general body meeting is going to be 2 weeks from today in the same room, actually, at the same time. So a little bit of consistency there. Remember, if you're interested in those individual projects, come talk to me. If you want to go to Crystal's meeting and then talk to me after that, that's fine too. Does anybody have any questions overall with anything? Cool. Thank you all for coming.
If you're interested in flight dynamics, testing,